That's what I say. It's like way out of it. That's what he said.
Okay. Yeah, we're Western.
That's what I said. It's like, I missed it.
So we did capillary bed and then capillary exchange, and now we're on capillary dynamics. This slide is a summary of why capillaries are perfect for their job, which includes huge surface area. They have really small diameter, so a very short diffusion distance. Their walls are extremely thin, basically just endothelium, right, with variable amounts of underlying connective tissue. Extensive branching means that most cells, most not all, because remember some cells, some tissues are not vascular, like epithelium is avascular, cartilage is avascular, but most cells are within a millimeter away from a capillary, very close to the blood supply. And then at the top, with the capillaries right in the middle of the picture, we can see that blood flow through any part of the circuit is the same. The amount of blood flowing through the aorta is equal to the amount of blood flowing, not through one, but collectively all the arterioles. Right? Or is equal to the amount of blood flowing through collectively all the capillaries. Okay? And that's important to note. We can't say that 5 liters per minute goes through the single aorta and 5 liters per minute goes through a single capillary. You can't make that connection. Because remember, the aorta diverges and it branches into many. So we're looking at flow through all of the branches at the same time. So 5 liters per minute is going through the aorta, is going through the medium-sized arteries collectively, the small, the arterioles, the capillaries, and so on. As that 5 liters per minute goes through the capillaries, all of them collectively, if you look at flow in any one of those capillaries, the velocity is extremely small. Very low velocity, just trickling through. Now collectively, you add up all of the capillaries in the body, it adds up to 5 liters moving through them in 1 minute, right? But the amount moving through one is a very small amount moving very, very slowly. So we have ample time for exchanges to take place. So you can see that velocity is at its lowest when blood goes through capillaries. Surface area is at its greatest. And the larger the surface area, the more exchange that we can carry out. And then flow is the same no matter where you are in the system. So now we are looking at the movement of fluid and substances across the capillary wall. There's 2 ways to move substances, solutes, across the capillary wall. One is diffusion. And all you need for that to take place, permeability and a concentration gradient. So if you're looking at glucose, for example, as long as there's a gradient for glucose to go from the blood out of the vessel, across the wall to the tissue, fluid tissue cells, then the gradient has to favor that. You have to have higher glucose concentration in the blood, lower in the interstitial fluid on the other side of the capillary wall. The other thing you have to have is permeability. Physically, glucose has to be able to get across the wall. Even a continuous capillary, which is the most, I don't want to say impermeable, the least permeable, right? Continuous capillaries are the least permeable of all capillaries. They still let glucose, and anything smaller than a protein for that matter, through. And water. And that's the other way glucose or any other solute could get through. By itself, through diffusion, by passing between endothelial cells, those spaces, those intercellular clefts, or get carried out with water. That's called bulk flow. So water has one way across, through the gaps between endothelial cells. It's called bulk flow. And with it, whatever's dissolved in that water, it's moving as well. like glucose. But solutes like glucose can also move by themselves by diffusion. Bulk flow just refers to the movement of fluid across the capillary wall. It doesn't tell you the direction. If bulk flow is directed out, it's called filtration. If bulk flow is directed into the capillary, it's called reabsorption. So over here, we're distinguishing between the different substances that may be moving across the capillary wall. If we're moving lipid-soluble substances, lipophilic solutes, they don't need to go between endothelial cells. They can go right through the endothelial cell because they're lipid-soluble. They go right through the lipid bilayer. So it really doesn't matter how big the clefts are between endothelial cells or how big the pores might be if it's a fenestrated capillary. Lipid-soluble solutes can always get through. Water-soluble, now you may be restricted. Whether or not you get through depends on the space between endothelial cells. Or if there happen to be pores, if you can fit through those pores or fenestrations. And for the most part, you can assume anything smaller than a protein can get through intercellular clefts or pores of a fenestrated endothelium. If you're too big to get between the cells or through the pores, like a big protein like insulin, for example, and let's say we're dealing with a continuous capillary, not fenestrated, right? So continuous, typical protein can't get through. Well, then you're going to have to use transcytosis. So insulin is inside the blood. It's trying to reach its target cell. Endocytosis on the luminal side, movement across the cell in the vesicle. Vesicle fuses with the basolateral membrane and then releases the insulin by exocytosis. Now, collectively, what we have done is transcytosis. And then, like the solutes, water has to get between endothelial cells or move through pores or fenestrations within the endothelial cells. But water cannot simply go across the endothelial cell, not like the lipophilic substances. On the right, they're showing us movement of water and small solutes dissolved in it, moving through the capillary wall between cells. That is bulk flow. They're also showing diffusion of small non-protein solutes moving between those endothelial cells as well. The pressure responsible for bulk flow, hydrostatic pressure, and oncotic pressure. Those are the pressures involved in fluid movement. As far as diffusion of a solute, it's just a concentration gradient. All right, so now we're going to look at the forces involved in bulk flow. We have two outward directed forces and two inward directed forces. What do you call the fluid pressure that's exerted on the inside of the capillary wall, pushing fluid out? Hydrostatic pressure of the capillary. In other words, blood pressure. Blood pressure is a type of hydrostatic pressure, a fluid pressure. And remember, hydrostatic pressure simply means fluid pressure exerted against the walls of its container. Here, the container is the blood vessel, the wall of the blood vessel, and the fluid is blood. So blood pressure is the force exerted by blood on the walls of the blood vessel. And it's directed out. You also have a lot of proteins in here, plasma proteins. And in comparison, very few proteins out here. So that creates an oncotic pressure. It is a type of osmotic pressure, but the difference is osmosis is usually due to small non-protein osmotic solutes like glucose and salts. However, non-protein solutes are free to move across the capillary wall and therefore distribute themselves evenly across the capillary wall. If the blood arrives and the glucose concentration momentarily is higher inside than it is outside, what's glucose very quickly going to do? Move down its gradient to the outside until equal in concentration. And that would be true for any solute smaller than a protein. Free to move across the wall and distribute itself evenly. So salt and glucose and everything else is going to be equal on both sides, so it's not going to generate an osmotic pressure. But the one thing that we can trap on one side of the capillary wall, because it's too big to pass through, is proteins. So we're left with only proteins exerting an osmotic pressure. And when that's the case, you can call it colloid osmotic pressure or simply oncotic pressure. And I think in the book they call it colloid osmotic pressure, which translates to osmotic pressure due to proteins. Remember, the difference between a colloid and a solution is proteins. Colloid has the proteins, the solution does not.
So you said colloid osmotic pressure?
You can call it colloid osmotic pressure or simply oncotic. And this would be oncotic pressure originating in the capillary. Oncotic pressure of the capillary, because that's where the proteins are concentrated, in the capillary. The few proteins that are out here in the interstitial fluid do create a very weak oncotic pressure that pulls water back out, right? But it's very minimal. This would be oncotic pressure of the interstitial fluid. Now the fourth force, also very weak, and typically about zero. Just like oncotic pressure of the interstitial fluid is usually about zero, this hydrostatic pressure in the interstitium is usually about zero as well. When would hydrostatic pressure of the interstitial fluid be greater than zero? When you have edema. Or if you put on a compression sleeve because you're trying to reduce edema in a limb, like compression socks or a compression sleeve on the arm, then you would generate some hydrostatic pressure in the interstitial fluid. And that's how the compression sleeve works, by the way. It increases the inward directed hydrostatic pressure interstitial fluid. It takes some of this excess filtrate and moves it back into the blood vessel to help reduce the edema. Okay, but you have two very strong pressures: hydrostatic pressure of the capillary, oncotic pressure of the capillary, and two weak pressures that are usually zero. So in the end, it typically comes down to these two. If hydrostatic pressure is greater than oncotic pressure, you end up with net filtration. If oncotic pressure is greater than hydrostatic pressure of the capillary, you get net reabsorption. Right? Again, that's assuming these two are zero, which typically is the case. If you're going to crunch the numbers, you're always going to set up your equation so that you're looking for filtration. You're calculating for filtration, which means you have to take the outward directed pressures, the ones that promote filtration, so hydrostatic pressure of the capillary, and add to that oncotic pressure of the interstitial fluid. And together these represent your outward directed pressures, the ones that promote filtration. And then you need to subtract from that any inward directed pressure. And the two inward directed pressures are hydrostatic pressure interstitial fluid and add to that oncotic pressure of the capillary. These are your inward directed pressures. And if you take out minus in, then you're left with your net filtration pressure. Now what if the outward directed pressures add up to 15 and your inward directed pressures add up to 25? What would your net filtration pressure be in that case? Minus 10, negative 10 millimeters of mercury. That doesn't actually mean that you have a negative pressure. You have an absolute pressure of 10 millimeters of mercury of force. But what's the direction? Is that directed in or out? In. So you're not actually getting filtration. What are you getting?
Reabsorption.
Reabsorption. So if you have a negative value for your net filtration pressure calculation, then you don't actually have filtration, you have reabsorption. But as long as the outward directed pressures are greater than the inward, and you end up with a positive value, then you actually do have filtration. What if your outward is 25 and your inward is 25? What if they match? What's your net filtration pressure?
0.
So there's neither filtration nor reabsorption. Positive value, you actually have filtration. Negative value, you actually have reabsorption. 0, neither. No bulk flow. Right, and again, that's the difference between filtration and reabsorption. It's bulk flow either way, it's the direction that's different, that's all. Filtration means the fluid's coming out, reabsorption means the fluid's going into the capillary. So let's crunch some numbers. On the study guide, and on this slide, you've got 35 for hydrostatic pressure at the beginning of the capillary, the arterial end. 17 at the end of the capillary, the venous end. And remember that blood pressure does drop as you move through the capillary bed, from the beginning to the end. And that's why you have two different pressures here. Oncotic pressure, interstitial fluid 1. Hydrostatic pressure of the interstitial fluid 0. Oncotic pressure of the capillary 26. So go ahead and calculate net filtration pressure. Should be hearing a question. I haven't given you enough information, so if you're calculating, I don't know what you're calculating. I'm waiting for the question. Do I want you to calculate net filtration pressure at the beginning of the capillary or the end? How about the beginning? And the reason I bring this up, about half of you on the exam, when I ask you to calculate net filtration pressure, will use both the 35 and the 17 and get really creative and add them together or take the difference or do something weird with them. And it doesn't work. You can only use one. So you need to know, am I asking for net filtration pressure at the beginning or am I asking for it at the end?
So you said the beginning?
So let's calculate it for the beginning. NFP at the beginning of the capillary. And then calculate it for the end of the capillary. So for the beginning, what's your two outward directed pressures? 35 plus 1. So you got 36. And then what are your two inward directed pressures? 0 plus 26. So the answer? And put the positive sign there. Put plus 10. And the plus is reminding you that you're actually getting filtration.
You want to put the millimeters of mercury too?
At a pressure of 10 millimeters of mercury. Right, those are the units. Positive 10 millimeters of mercury in pressure. Net filtration pressure at the end. So you only need to change one value, right? Just replace the 35 with 17. So 36 becomes,
18.
and net filtration pressure becomes,
Negative.
negative 8. So the negative sign tells you you're actually getting reabsorption. Negative filtration means reabsorption at a pressure of 8 millimeters of mercury. And it's true that along the first half of the capillary, we actually get filtration. But along the second half, we're getting reabsorption. And the filtration tends to be a little greater than the reabsorption, adding up to about 2 to 3 liters of excess filtrate accumulated in our systemic tissues each day, which gets picked up by the lymphatic system and returned back to the bloodstream. What would hydrostatic pressure have to be to have neither filtration nor reabsorption, but just to find the transition point, somewhere in the middle of the capillary? What would it have to be? So these aren't going to change. Hydrostatic pressure, interstitial fluid, oncotic pressure, capillary, the 26 is going to be 26. Oncotic pressure, interstitial fluid is 1.
It's 25.
It needs to be 25.
So what do we have to add to 1 to equal 26?
25.
There you go. So we've got a pressure at the beginning of the capillary of 35. At the end, was it 17 I gave you? Yep. And in the middle, 25 is going to be that transition point. Based on these numbers. Does that make sense? So along the first half, are you getting the greatest filtration at the very beginning or towards the end of the first half? Right? So as you move across, net filtration is decreasing. Starts at the highest point and then drops until we get down to an NFP of 0. And then from there, -1, -2, -3, -4, -5, all the way up to -8. So along the second half of the capillary, what's actually happening is all reabsorption. But we don't reabsorb all the fluid that we brought out through filtration in the first place. So we end up with net filtrate remaining that has to be picked up by the lymphatic system. Another way to look at what's going on, what's changing, what's not changing. Let's look at all these pressures over distance. So we're basically looking at net filtration pressure along the length of the capillary from the arterial end to the venous end. To simplify this, let's make hydrostatic pressure of the interstitial fluid 0, which it typically is. And let's make oncotic pressure of the interstitial fluid 0 as well, which it typically is. There shouldn't be any significant amount of protein accumulating in the interstitial. In fact, that's one of the jobs of the lymphatic system, to pick up not only the excess filtrate, but the proteins as well, so that they don't accumulate. And unless you have edema, there should be no significant hydrostatic pressure in the tissue fluid. It should be about 0. So that leaves us with just 2 things to consider. Blood pressure, which starts out at 35 at the beginning of the capillary, but by the time we get to the end, it's down to what?
17.
And then we have oncotic pressure of the capillary, which is about what? 26? And that one doesn't change. As long as hydrostatic pressure of the capillary, your outward force, is greater than oncotic pressure of the capillary or inward force, what's actually happening? You're getting net filtration. But that net filtration pressure is dropping only because blood pressure is dropping. So when blood pressure hits 26, now the outward pressure and the inward pressure match, and there is no net filtration or reabsorption. Right? That's our transition point right in the middle. But once we pass that, and now blood pressure is lower than oncotic pressure, what starts to happen?
Absorption.
Net reabsorption. We're going to see a negative net filtration pressure. That becomes stronger and stronger as the blood pressure drops lower and lower. And again, if you add it all up, the amount of filtration that's occurring along the first half does exceed the reabsorption along the second half, leaving us with net filtrate formation when all is said and done. Make sense? This is the focus figure from the textbook. They use the same equation I do. Right, so if you need a reference, you want to practice crunching the numbers, you can use this as an example. They used to use a different equation that's very confusing. So if you're using the 9th edition or earlier, you're going to see a different equation. One that combines the oncotic pressures and then combines the hydrostatic pressures, and it's very illogical, unintuitive. And I complained, and I'm sure others complained, and they changed it to this very simple one. Net filtration is slightly larger than net reabsorption, so about 2 liters of fluid per day escapes the capillaries, but is returned to circulation by the lymphatic system. Benefits of these net filtration fluid movements from blood through the interstitial fluid to the lymphatics and back to the blood. And we've talked about this. How plasma becomes interstitial fluid becomes lymph, and lymph once again becomes plasma. Benefits. 1, enhanced delivery of substances to the tissues. Right, so one way to deliver glucose to the tissue is by diffusion, but the other way is bulk flow. Right? And net filtration refers to the bulk flow. Net water with glucose dissolved in it, moving across the capillary wall into the tissue fluid. Number 2, continuous mixing of the ECF divisions. Mixing of plasma and interstitial fluid, lymph, plasma. The benefit is you don't have to monitor those 3 different environments. You don't have to monitor the composition of plasma separate from the composition of interstitial fluid, separate from the composition of lymph, because you know they're all the same. They're all the same with one exception, cells, proteins. But aside from cells, proteins, which don't cross the capillary wall, everything else is the same, including the temperature, right? The osmolarity, the pH, oxygen, CO2. So what do we measure? What do we monitor? If you look at all the receptors in the body, the receptors that monitor all these different homeostatically regulated variables, what fluid environment are they actually monitoring? Blood, plasma. Think about the names of these homeostatically regulated variables. Blood oxygen, blood CO2, blood pH, blood osmolarity, blood volume, blood pressure, blood temperature. You see a common theme? Blood. And then The job of the organ systems is to make adjustments to blood composition. But in doing so, what else are we fixing if there's a problem? We're fixing the lymph, we're fixing the interstitial. And when you add those three together, plasma, lymph, and interstitial fluid, that's 90-something% of all of our ECF right there. So we only have to monitor one of those environments, we only have to make adjustments to one of those environments, and that's the benefit of them constantly mixing together. If there's a problem in one, there's a problem in all. You fix it in one, you fix it in all. Number 3, transport of larger, insoluble substances to blood. So what example are we really referring to that you learned about in lymphatic system chapter? What are we using lymph to deliver to blood? Chylomicrons. Yeah, fats. So when we digest and absorb lipids and lipid-soluble substances like lipid-soluble vitamins, A, D, E, and K, all of those things come across the luminal membrane of the intestinal epithelial cell. Inside of the cell, we take the fatty acids, and we take glycerol, and we reform triglycerides, and we take cholesterol and phospholipids and everything that's lipid-based, and we combine it into this huge round structure called a chylomicron. And the outside of the chylomicron is water-soluble, and that's achieved by putting all the proteins on the outside and all the phosphate heads from all the phospholipids. Right? Those polar heads can interact with water. So now we've created a shell that is totally water-soluble, which means the whole thing is now water-soluble. The only problem is when we move it across the basolateral membrane of the intestinal epithelial cell, it's too big to get into a blood capillary. So instead it goes into a lymphatic capillary. Right? But again, the benefit of all this is plasma becomes lymph, plasma becomes interstitial fluid becomes lymph once again becomes plasma. So we can put these chylomicrons in the lymph, and we know it's going to end up in the bloodstream. And number 4, flush microbes and toxins into lymphatic tissues, where we house the bulk of our immune system. Because we're constantly forming excess filtrate and having to move it from the interstitium into the lymphatics, that doesn't allow things to just sit in the interstitium, like toxins and bacteria and viruses. We're flushing them out, right? They're getting dissolved in the water that's getting picked up by the lymphatic capillaries. So we're taking all that stuff and we're moving it through the collecting system. But as it goes through the collecting vessels, remember it's going to go through lymph nodes along the way. And what's going to happen is we move all these toxins and microbes and debris into the lymph nodes. What do the lymph nodes do? Clean it out, right? They clean, they filter the lymph. And indirectly, in doing so, clean and filter plasma. Because lymph was interstitial fluid, which was plasma. What would be the consequence of reduced plasma proteins due to liver disease or starvation? So either the liver has the raw materials to make the proteins, but the cells are not able to make them because of liver disease, or we don't have the raw materials because of starvation. Either way, what's the consequence of reducing the number of plasma proteins? Which one of these pressures is determined by plasma proteins? Is that an inward or outward directed pressure? And with liver disease, is that pressure becoming greater or smaller? So if you reduce one of your inward directed pressures, what happens to NFP? It goes up. So now you're forming more filtrate across all your capillaries on a daily basis. And now maybe the lymphatic system can't keep up. So what starts to happen? Edema. Right? That is the consequence. Edema. And the problem with edema is there's so many different things that can cause it. It's not an easy diagnostic tool. It's not like you come in, oh, you've got edema. Well, this is the problem. It could be liver disease, it could be hypertension, it could be an abnormality in the lymphatic system, a blockage, compression of the lymphatic vessel. There's lots of possibilities. And we did talk about lymphedema. If the edema is called lymphedema, what exactly is the problem? What's causing the swelling? It's not that you're making too much filtrate. That hasn't changed. The lymphatics aren't able to pick it up and remove it, right? Either because the lymphatics have been removed, which sometimes happens, when we have like removal of breast tissue after a mastectomy. We have to remove some of those lymph nodes and lymphatics as well, thinking that maybe the cancer spread in there. We want to remove all that. Or maybe compression from a tumor, right, or a blockage of some kind. But yeah, something's wrong with the lymphatic vessels. Venous system. We can do that after break. Start venous system after break.